Many scientists dismiss the belief in the curse of the cover of Sports Illustrated as a misunderstanding of a phenomenon known as regression to the mean. And this means the regression to the mean refers to the fact that extreme observations of statistics measuring performance for any given athlete or team are more likely to be followed by observations closer to the average than they are by more extreme observations. So this means that athletes with high variation in performance stats are more likely to have a large drop in performance after an outstanding performance than they are to sustain a high level of performance. Let's look at the distribution of player performance statistics. For any performance statistic, the value observed for any given athlete from week to week is a random variable. Here we show some statistics for Michael Jordan and Scottie Pippen. On the left, we have field goal percentage for both players per game for about 200 games. So on the left, we have the variables x and y. X is the field goal percentage per game for Michael Jordan, and y is the field goal percentage per game for Scottie Pippen. And we put these in Stata, a software package, and converted the data into the best estimate of a density function for these statistics for both players. On the right, we have the number of points scored per game, and again this has been converted to a density for the data by Stata. These statistics were collected by Peter Ulrichsen, who's a graduate student at Notre Dame. And we have on the left for x the field goal percentage. For Michael Jordan, its expected value, or the center of that distribution, is at 0.48 approximately, with a standard deviation of 0.1. And we see that the density function for y, the field goal percentage for Scottie Pippen, is a bit wider with a larger standard deviation of 0.13, but the expected value is roughly the same as that for Michael Jordan. On the right-hand side, we have the z is the number of points per game for Michael Jordan. The expected value is about 29.59. And the standard deviation is about 8.44. And now for Scottie Pippen, W is the number of points per game for Scottie Pippen for these 200 games. The expected value is approximately 19.67. So this is significantly lower than the number of points per game, the average number of points per game for Jordan. And the standard deviation is approximately 7.28, which is roughly the same as Jordan's standard deviation. We see that for any given statistics measuring performance, the distribution is going to vary from player to player. Players who have a high average and a low standard deviation have consistent levels of high performance, whereas players with a relatively low average and a high standard deviation will reach high levels of performance, but less often than those in the previous category. Let's have a look again at the points per game for Michael Jordan and Scottie Pippen. Let's try to use the density functions shown above to estimate the percentage of time that the number of points per game was above 30 for both players. Now, I would advise you to try to figure this out on your own before I show you the solution on the next slide. Okay, so let's try to solve this problem. How are we going to get that the probability that each player for a randomly chosen game, the probability that their points in that game was greater than 30? Well, recall that the probability is going to be the area under the density function to the right of 30 for both players, and the total area under the density function is going to be 1. So for Michael Jordan, we have the density function is here, and the probability that Z is greater than 30, Z is the number of points per game for Michael Jordan, is the area under the density function to the right of 30, which is the area under that density to the right of this vertical line. So we see that more than 50% of the area under that density function lies to the right of 30. So this means there was a probability of probably around 0.55 that any given game or any randomly selected game of Michael Jordan's from those 200 would have a score of more than 30 points. For Scottie Pippen, the probability that the number of points scored was greater than 30 is the area under this density function to the right of 30. And now we see that a much smaller proportion of the area of Scottie Pippen's density function lies to the right of 30. By my estimates, it's about maybe 20 to 22% of the area under that density function lies to the right of 30. So I would estimate that the probability that a game chosen randomly has a score greater than 30 for Scottie Pippen is probably around 0.22, which is much smaller than the probability, the corresponding probability for Michael Jordan.